Hey everybody! By this point you've seen the new AP Physics C topic list. I just want to quickly talk about what the test format's going to look like. Um, the official test format won't be released till April 3rd, but what I will guess is that much more of it will be, well, first of all, it's all free response question, no multiple choice. But I would expect that every single question would have some sort of narrative. Explain how you would do the following. Describe how you would design a lab that would test for the following. Why? That kind of thing is very easy to check for copy pasting from some other source um, than a simple mathematical question. So we'll spend some time on it. We're almost done with rotation. We've got one more lecture after this, and then we'll start reviewing, and I'll give you some more hints about that then. So tonight, angular momentum, or today, angular momentum and rotational kinetic energy. Just a quick reminder again, regular momentum is mass times velocity. Angular momentum is a vector quantity as well, equal to I times omega. This is not a dot product or a cross product. It's simply just a multiplication. This is a scalar. This is a vector. This is just the scalar times the vector. Just like force can be written as a change of momentum with respect to time, torque can be written as a change in angular momentum over time. I just want to mention just real quick in passing, if this is true, then also therefore torque times dt is equal to dl, or the integral of torque dot dt gives you the change in the angular momentum. If torque varies with time, you have to use this form as opposed to a simple delta t. As long as there's no external torques, the angular momentum is constant. Just like if there's no external forces, momentum is also conserved. Angular momentum is one of those big three in physics that are conserved quantities: conservation of energy, conservation of momentum, and conservation of angular momentum. Just want to mention also in passing, this is the general form of angular momentum, but there's a special case when you're working with discrete or individual masses. That is, angular momentum is equal to r cross mv. If you're only interested in the magnitude of it, you can just use r, radius times mass times velocity times the sine of the angle between these two quantities. Mass doesn't have a direction. Or you can just use the r perpendicular to the velocity, and that also works. Just remember, like torque was like that as well. So how do you solve this real quick? If you're interested in the angular momentum of this mass m relative to this asterisk over here, how would you do it? You draw a radius vector from the asterisk over to where the mass is, and you would also be interested in the theta, which is the angle between these two vectors. So you would just take the radius times the mass times the velocity times the sine of the angle. Or you can do this. If you draw a line back from the velocity, along the line of velocity, and figure out the radius that is perpendicular to that line that goes through the velocity, you can just take this distance times the mass times the velocity, also gives you the magnitude of the angular momentum. I should mention this real quick. Angular momentum is a vector quantity. It has a direction. If you do your right hand rule, where you point the palm and fingers of your right hand along this radius vector, and then if you can easily bend your fingers in the direction of this velocity vector, your angular momentum vector is pointing in the direction of your right thumb. If you check this real quick, if you do r cross v, you should discover that your thumb is pointing out of the screen or in the positive z direction. And so this object has positive angular momentum relative to this point. All right? It's kind of cool. Two quick videos. Normally we do these as demos in class. Some of you might remember from last year. Ice skaters, what happens? When ice skaters have their arms extended, they have a large rotational inertia and a small omega. When they pull their arms in, it reduces the rotational inertia, remember, is equal to mr squared. The mass of their arms gets a smaller radius, which means omega gets larger. In this case, if you're standing on a rotating platform and you've got a spinning bicycle wheel, if you suddenly rotate the bicycle wheel over, its angular momentum is now pointing this way, which means your angular momentum has to be equal in magnitude to 2L, me pointing this way, so that the total angular momentum before and afterwards is conserved. I've got two videos real quick to show you these because I'm not actually, because we can't demo these in class.
And is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Which is pretty fun. Sorry, I missed the audio the first part. I realized I had my headphones plugged in. And then I'm going to show you the spinning wheel.
2, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same.
Actually, in this
So when you
case,
flip
no
this thing
external
over
net torque.
and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
And hopefully that helps a little bit. There's a few mistakes in the video. It's from MIT, but it's still fun. He uses, yeah, it's good. I want to show you an AP problem that involves angular momentum. We've got a bunch more in this chapter. There are, in a normal AP year, a very high probability of a problem involving angular momentum. But let me show you this one real quick. A spacecraft of mass 1,000 kilograms is in an elliptical orbit about the Earth as shown. At point A, the spacecraft is at that distance and has a magnitude of velocity of that. The mass and radius of the Earth are that and that respectively. Determine each of the following for the spacecraft when it's at point A. In other words, when it's over on this side of, or when it's right here. The total mechanical energy of the spacecraft, assuming that gravitational potential energy is zero at an infinite distance from the Earth. And you might say, whoa, 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 this is really complex. It's not. Mechanical energy is the sum of the kinetic and potential. And by defining the energy zero at infinite distance, we can use the standard form of GPE, the big form, which is negative G m1 m2 over r, not r squared, that's the force one. Kinetic energy is that. Plugging in our numbers, we get this. I didn't write out G just for space considerations. And if you solve it, you'll end up with that minus that, or negative 8.15 times 10 to the 9 joules. You might say, what, negative? How can energy be negative? Well, believe it or not, this satellite is trapped around the Earth. It can't escape because it has a deficit in energy. Remember, we talked about this a little bit before. Reason our atmosphere is stuck here is because it has a deficit in energy. This satellite's still trapped in orbit around the Earth because it can't quite escape. And now here's where the angular momentum comes in. The magnitude of the angular momentum of the spacecraft around the center of the Earth. How do you do that? This is a point mass, and so I'm just going to take R cross, or sorry, actually, R cross MV. In this case, though, this is nice. This is perpendicular, so I don't need to worry about the sign. And since I'm only interested in the magnitude of it, I can just do MVR sine theta. In this case, theta is 90. So, or just doing it that way. Plugging in our numbers, it's just that distance times the mass of the spaceship times, did I put it in the wrong order? The velocity is, yeah, that's right. Okay, times the velocity. Or you get that. Units for angular momentum, kilogram meter squared over seconds. Some of you might say, wait a second, shouldn't it be, since rotational, sorry, let me write it real quick. Since rotational inertia is measured in kilogram meter squared and omega is measured in radians per second, shouldn't L have units of kilogram meter squared radians over seconds? But again, remember, radians don't really exist. And so when you multiply this out, it just ends up being this term. Okay? And now the second part of it. Later, the spacecraft is over here at point B. Again, nicely perpendicular. On the opposite side of the orbit, at a distance that from the center of the Earth, determine the speed of the spaceship. And you might say, oh man, this is going to be really, really hard. But here's where conservation of angular momentum makes it super uber easy. Solving this one, we know that the angular momentum has to be conserved. That's what its magnitude was just in question B. And so in this case, our new distance now is this. The mass spaceship is still that. And we're looking for how fast it's moving over here, V sub B. Solving this really quickly, you'll discover that it's moving much slower over here than it was moving over here. And you'll discover that's true for any orbit. As things move away from the thing that they're orbiting, they tend to lose velocity as they gain GPE. So they're losing kinetic energy, but gaining GP. It's further away from the center of the Earth. And as it falls this way, it converts GP back to KE. And that's why planets move faster when they're closer to the sun. All right, next part. Suppose that a different spacecraft is now put back at point A, and that distance, determine that the speed of the spacecraft, it's in circular orbit. So what if we put a spaceship here, and we went to go into a circular orbit around the Earth? What speed would it require? Well, if you remember, the requirement for circular orbit is that the gravitational force has to equal the centripetal force. And you're like, oh, good, mg equals mv squared over r. Well, remember that gravitational force does change as you move far away from the planet. In this case, we're definitely far away. So we have to use the sort of more general equation, g m1 m2 over r squared. And technically, I know there's a negative here, but I just want the magnitude of the gravitational force to equal the magnitude of the centripetal force. And I'm using mv squared over r. Why? Because I'm looking for velocity and I know the radius. And if you solve that, you'll discover for a circular orbit, it's this speed. Now, some of you might be saying, wait a second, Mr. Clemmer, I thought you said that for a circular orbit around the Earth, it's about 8,000 meters per second. Yeah, that's really close to the Earth's surface. In this case, we're actually quite a distance away, so the velocity required is smaller. And then part E, the minimum speed of the spacecraft at point A if it's to escape completely from the Earth. What are they talking about here? They're talking about escape velocity. What's escape velocity? Well, with escape velocity, you have enough speed so that as you leave the planet, you keep losing speed, but you don't stop. Your velocity doesn't become zero until you approach, I don't know how to write this nicely, approach infinity. In fact, your velocity only drops to zero at infinity officially. So how do we solve this one? And by the way, this is a mechanics level 3. It's supposed to be kind of hard, and this is the last question on it. How do we solve it? The same way. We need the total energy to be zero. Do you remember when we solved this on the first one? We had a deficit in energy. That's what kept it in orbit. So for something to reach infinity, it needs to have enough kinetic energy to offset the deficit in gravitational potential. So in other words, 1/2 mv squared plus the deficit in GPE must equal 0. And if you now solve this is just a quick plug and chug now, you'll discover the escape velocity is about that. Once again, you might say, wait a second, Ms. Clemmer, I seem to remember last year in AP Physics 1, you said that from the surface of the Earth, the escape velocity is about 12,000 meters per second. Why is it so much smaller here? Because I already have a bit of a head start. I'm not starting all the way from the surface of the Earth. I'm already at some distance above it, and so I only need to move this fast from this one. What direction do I need to move? Any direction, as long as I have the magnitude of this velocity. Cool. All right, precession. If you take a bicycle wheel, and some of you remember me doing this demo, give it a spin and hold it from one end, Instead of falling over, it actually precesses. And I want to spend just a moment talking about that in another video.
Nothing special about a wheel that's not spinning. Forget to hold it up, and it'll fall over like anything else. The force of gravity naturally tips the wheel down. In other words, if the wheel doesn't spin, it has no place to go but down. But a spinning wheel is quite another matter. A spinning wheel has angular momentum, and remember, there's that strange twist when momentum's angular. It's not the force that changes angular momentum. It's the twist. If R cross F equals 0, the angular momentum is conserved. Obviously, not all forces behave that way. For example, to open a valve or to get a wheel rolling, twist is just what's needed. Torque is the twisting force that causes rotation, and it's equal to R cross F. But a spinning wheel is already rotating. It has angular momentum to start with. Now, torque can make that angular momentum change, but in a different way. In fact, now gravity can play a strange trick. Its force is downward, but the torque is sideways. According to the equation tau equals dl dt, the angular momentum will rotate sideways. And rather than fall down, so will the wheel itself. So in a roundabout way, it's easy to illustrate the fact that a spinning wheel doesn't fall. But beyond this example of life-copying animation, what's really going on here?
So this kind of motion is called precession, and it's one of the stranger ones, but it's kind of fun to look at. So take a look at this. How do we calculate the precession? Well, again, remember what's going on here. We're holding it or pivoting it at one point over here. I guess actually the way I drew it here. And the force of gravity is acting down at the center of mass right here. This torque, R cross F, is producing, if you check it with your right hand real quick, a torque that's directed into the board. So drawing my little torque vector here, it's going into the board, R cross F. What's that going to do? The angular momentum at the wheel spinning this way, if you check with the other right hand rule by twisting your fingers, you'll discover the angular momentum vector is pointing out this way. What's going to happen here? R cross F, torque's pointing. Wait, did I do the wrong way? R cross F. No, it's pointing into the board. What's that going to do? It's going to redirect this thing this direction. And what's going to happen? My new torque vector is going to be pointing in here. I've got it drawn a little bit differently down here. I don't know why it's backwards. That's kind of strange. It's all right. Solving this real quick. So just to clarify, just so we don't get confused, normally we use omega for the angular velocity. I'm going to use capital omega for the rate of precession. Again, it's measured in radians per second. It's how fast this thing is going to be moving this way. Why am I using a different omega here? Just because this wheel already has some omega, and I don't want to confuse this omega with the spinning wheel's omega. So it's going to be equal to d theta over d time. So theta is how much this thing moves per unit time. And now I'm going to do one little quick cheat here. Remember that theta in radians is equal to arc length over the radius. And I know you're not going to be happy with this. I'm going to say the arc length here is dl. And I could use either one of the sides here, but I'm going to say the radius is L. What's the bad news about here? So what's the argument? Well, dl here is actually not an arc. It's a straight line. But again, if I let delta t approach 0, this approximates a straight line. Why am I using this side and not this side for my radius? This one's probably a little bit easier to work with. All right, so solving this one. What's d theta going to be? Well, d theta is dl over L, and I didn't write an extra delta in front of this because it's just too much, all over time. Or rearranging it, moving the L to the bottom, I get delta L over L times delta T. And the L here, the original, it would be L original down here, but I'm leaving it out. Now remember from what I told you about beforehand, change in angular momentum is equal to torque times time. And I know I didn't write it in calculus notation here, but forgive me. Which means I can rewrite this way. So replacing delta L with tau times delta T. Nice thing about this, delta T's actually switch or cancel out, which leaves me just tau over the angular momentum. Plugging in, or just remember the torque on this thing is just R cross mg, in this case the angle is 90. So the torque is just R times mg. Plugging in my numbers then, I get this. The torque is mgr, and the angular momentum is I times omega, where omega is the initial angular velocity of the wheel. What's the rate at which the bicycle wheel precesses? Well, it depends on the torque and inversely to the angular momentum. The faster the wheel's spinning, the slower it precesses. And you've seen precession before with, like, for example, toy tops. If you don't know what a top is, it's one of the, like, this looks more like a dreidel, where you get this thing spinning, and instead of falling over, it slowly precesses around in a circle. As it slows down, the rate of precession increases until it finally falls over. So as omega of this thing gets smaller, this omega gets larger, the rate at which it precesses. All right. This also explains Kepler's third law in terms of angular momentum. Kepler's second law says that a line that connects the planet to the sun sweeps out equal areas in equal times. When it's far away from the sun, the velocity might be this. The area it sweeps out in some small amount of time would be this. When it's close to the sun, that planet is going to have a much larger velocity, and so it may sweep out this much area in the same delta t. What's true about this area compared to this area? According to Kepler, he said those two areas should be identical. Did he have any idea why? Nope, he just had observations. The reason why is the conservation of angular momentum. Just real quick, rotational kinetic energy, I know we've already talked about it. Regular kinetic energy is equal to that, and work is equal to force times distance. For rotational kinetic energy, 1/2 I omega squared, m becomes I, v becomes omega squared. And same kind of thing was true with work. Work, instead of being force times distance, becomes tau dot d theta. Remember that, that'll come in handy later. My dot product ended up missing here. Remember, you could write power as special case force times velocity. Same thing's true here. You can write power as tau, torque times omega. The work done is the change in the kinetic energy. So take a look at our problem again, the one we did last time. And let's start actually with the velocity after the mass is falling a distance h. I didn't do that last time because I was like, oh, this is going to be really messy. With energy, this one becomes much simpler. Take a look at it. Initial energy plus any work equals the final energy. In this case, the mass starts out with GPE. In the end, the mass as it falls is going to have lots of kinetic energy, and the wheel, which will be rotating, is going to have rotational kinetic energy. So that's going to be converted. So we end up with that. Remember, GP mgh equals 1/2 mv squared plus 1/2 I omega squared for the disk. Plugging in our numbers, since we know it's a disk, is just 1/2 mr squared. Remember again that we can do omega times r equals v, or omega is equal to v over r. Plugging that in here, I can do that. And this reduces very nicely down to that. I can cancel out the m's. Oh, no, I can't cancel out the m's. I'm so sorry. That's a different mass. That's the mass of the disk. Sorry. But what I can do is I'm looking for velocity. I can factor out the v squared from both of these two terms here. Give me this. Multiplying through by 4 gives me this, which makes it a little bit nicer in terms of fractions. And so I can come up with the velocity then is equal to moving this term to the other side. the square root of this, or you can move the 4 outside and give me this. And there's the velocity after it fell that distance. You might say, well, wait, is that much nicer? Yeah, because believe it or not, you can find the acceleration very nicely. Why? Because we know the final velocity. Initial velocity was 0. And we know the distance it fell was h. You could very quickly calculate the acceleration. And then once you knew the acceleration, you could very quickly calculate the tension. Why? Remember that mg minus the tension is equal to ma. And we know the acceleration from this part here. And so energy in some ways is simpler than doing the simultaneous equations. Oh yeah, sorry, I wrote that down there. Remember when we did things rolling down ramps? This is a sphere rolling down a hill without slipping. Mass m is initially at rest. It has some radius r, has a height of h. How do we solve the velocity at the bottom of the hill? Again, we use the work energy theorem. In this case, it starts out with GP. At the bottom of the hill, when it's down here, it's going to be both rolling and also moving translationally. And so it's going to have both kinetic energy and rotational kinetic energy. Plugging in our numbers, mgh equals 1/2 mv squared plus 1/2 I omega squared. Because it's a sphere, 2/5 mr squared, if you remember that. Again, doing the substitution, I can do the v over r, and it gets me down to this. M does cancel this time. Woohoo! It is the same m in all three terms. And so you can come up with that, or solving for velocity. For a sphere at the bottom of the ramp, it's the square root of 10/7 gh. That is not the same for other objects. Why? If this rotational inertia is different, you'll end up with a larger fraction of the energy. So if I is bigger, you'll end up with a larger fraction in terms of this and a smaller fraction in terms of that, or a smaller part of this. If I is small, you'll end up with a smaller fraction of this and a bigger fraction of this. How does that relate? Which is the fastest thing down the loop? Well, the very fastest thing is just a box sliding without friction. Why? Because there, all the GPE is converted into KE. The end here is the hoop. Why? Because its rotational inertia is mr squared. The solid cylinder 1/2 mr squared. The sphere 2/5 mr squared. You'll see them ranking in terms of the smallest rotational inertias will have a greater fraction of kinetic energy and therefore will make it down to the bottom with a greater linear velocity. At the bottom, they all end up with the same energy, but the fraction of kinetic compared to rotational kinetic energies change. We've done Atwood machine before, but what happens if the pulley, this thing here, has mass? If it has mass, it means it also has rotational inertia, which means we've got an interesting problem. The tension here is not equal to the tension on this side. Before, if we ignored the pulley and said it had no mass, we said these two are exactly equal to each other, the two tensions. But in this case, what must be happening here? It says M2 is greater, so this one's accelerating downward. This tension here has to be greater than this one so that there's a net torque to make this thing angularly accelerate this way. If these two tensions were the same, this thing wouldn't rotate or angularly accelerate at all. And we're assuming this rope is not slipping on this pulley. So how do we solve it? Because we have both linear acceleration and angular acceleration, we do it the same way as before, but things get a little bit more complex. Why? Well, for this mass, the force of gravity is, of course, m2 times g minus t2 equals m2 times a. And we can also do that for the other side over here. Force of gravity on this one is m1 times g. But in this case, the tension must be larger because it's accelerating upward. We're told that mass 2 is bigger than that one. But in this case, so t1 minus m1g equals m1, this mass, times its acceleration upward. They do have the exact same acceleration, but they have two different masses. Can I do anything with these two equations? The answer is no. I've got now these two equations, but I've got three unknowns. T1's unknown, T2's unknown, and the acceleration's unknown. 2 equations with 3 unknowns, not cool. But what I can do now is write this. This disk has 2 torques acting on it. T2 times the radius minus T1 times the radius. This torque is trying to rotate it this way. This torque is trying to rotate the other way. This one's going to win. It's got to be a larger torque because it's angular accelerating that way. Equals the rotational inertia of 1/2 mr squared times the angular acceleration alpha. Doing the quick substitution, you might remember again, I can do that. I can get down to this. You're like, oh, good, I can solve it. Well, believe it or not, I now have 3 equations with the 3 unknowns in them. And you're like, wait, there's tons of variables. Yeah, but I'm assuming M1, M2, and capital M are all known quantities, along with, I guess the radius doesn't matter. So, grabbing your TI Nspire, because I don't want to do 3 simultaneous equations, I'm going to tell it, hey, I want to solve these 3 equations, and I want to solve them for variables T1, T2, and A. And if you do that, it'll give you the symbolic results, which are just plain ugly, I'll admit it. The acceleration is equal to this, T1 is equal to that, and T2 is equal to that. Notice the denominators are the same in all 3 cases. Things just change a little bit on top. All right. It's probably one of the worst problems, but you kind of get the idea. If you've got pulleys which have rotational inertia, you're going to end up with 3 unknowns and 3 simultaneous equations, or a system of 3 equations to solve. Number 67 from your homework tonight. I just want to do this one. This is one that students normally ask, so I thought I'd hit this one ahead of time. A uniform circular spherical shell, I almost missed that, of mass m and radius that can rotate around a vertical axis on a frictionless bearing is shown. A massless cord goes around that over a pulley of rotational inertia, and radius, and is connected to a small object of mass there. There's no friction, the cord does not slip. What's the speed of the object when it has fallen that far after being released from rest? Use energy conservation or considerations. So I can just do this all in terms of energy. So solving this one, it's going to be the GP, I'm converting the GP of the mass, assuming that the bottom point, wherever it lands, is h equals 0. So it has some GP up here until it hits the ground. Is going to be converted into the kinetic energy of the mass just before it hits the ground, plus the rotational kinetic energy of the sphere, plus the rotational kinetic energy of this pulley, which is also going to be rotating. Man, we got a lot of things rotating. Plugging in what we've got this. So 1/2 mv squared plus 1/2 I omega squared plus 1/2 I omega squared. And I'm writing in units here just so we can remember what's what. And now just plugging in our numbers. Mass times gravity times the height change is going through. 1/2 times mass times its final velocity plus 1/2 times I. Remember, for a shell, it's 2/3 mr squared. And I replaced omega with v over the radius squared right away, times 1/2 I, and they gave us the I for the pulley, just literally plugging it in, times v over r squared. Well, that's the radius of the pulley. Simplifying that down, I really jumped that one fast. You'll get the final velocity is about 1.4 meters per second. All right. With that, hopefully you'll be able to do the other ones. We're going to start looking at a lot of AP problems in the next week or so once we finish this unit. So there are tons of AP problems to look at. With that, have a great night or a good day the rest of the day, and we'll talk to you soon. Bye.